is a collection of blocks, and a block is a collection of threads. Each thread is like a tiny processor with its own registers that can perform arithmetic, loops, and logical operations. In this matrix multiplication example that we present here, each thread is responsible for computing one scalar result, meaning one element of the output matrix. In general, each thread runs its own little program. It can read many values from memory, perform arithmetic and control flow, and cooperate with other threads in its block through shared memory and synchronization, and finally write one or more results back to memory. Okay, looking at this diagram, there's two items you put to describe the blocks and threads. We have block dimension of 3 by 3 and grid dimension of 2 by 2. In other words, each block is the blue, green, pink, and orange blocks. And you remember the hierarchy is that grid contains blocks which contains threads. Okay, so we have block dim 3 3 and grid dim 2 2. Okay, the position is indicated in the same normal XY coordinate system that you're familiar with math and so forth. So in this grid, the bottom right hand block, the darker orange thread, block IDX1, meaning the X coordinate in the set of blocks is 1. We start counting at 0, so it's the second one really. In block ID X, Y equals 1. Again, second row. Think of it like that. And then within each block we have the thread. Coordinates or location. Here it's the bottom right one, so it's thread IDX equals 2, and thread IDX dot Y equals 2. Bottom right hand corner. Okay, here this blue diagram, this is the diagram of what we're going to do here. We have a grid dimension 1 1, so it's just going to be one block. So we have one block of dimension 3 by 3. We just happen to make it that size to line up with the size of our matrices that we're going to multiply to make it a little easier to understand. So this gives us 9 total threads. So within each of these, you can see the thread location. For example, the one in the middle is thread IDX dot X equals 1, and thread IDX dot Y equals 1. So dim 3, here's another way to grasp the idea, because you can see a definite relationship between the two things, grid dim and block dim. So think of, for example, block dim AA. That's a block with A by A threads. And then if we say grid dim CD, that's a grid with C times D blocks. So you can calculate the total number of threads. It's C times D times A times B. You can see that they're related. So in our code sample that we give here, we have one block of 3 dimensions. So block dim will be 3 3. Grid dimension will be 1 1. So the total number of threads is 3 times 3 times 1 times 1. 9 threads. Makes sense? We're going to do matrix multiplication of a 3 by 3 matrix with another. That takes 9 discrete calculations. Each produces a scalar, which we plug into the outputting resulting matrix, which will be 3 by 3. That's the rules of linear algebra. We will explain to you if you're not real familiar, quickly, how that works in linear algebra. All right, here we define our kernel. We know it's the kernel definition because it has the underscore global tells the compiler that this function runs on the GPU and is launched from the CPU. Okay, we pass into it the parameters, pointers to A and B. We're going to multiply A times B and C. These are all locations in GPU memory. And then int will be the number of elements in each array. Okay, here now, the next thing is to calculate where we are in terms of threads. So remember, the kernel is going to call the kernel function multiple times. What's changing each time? The block dimension, the block location, and the thread location. So you have to keep track of that. So for example here, inside the kernel, the first task is to figure out which element of C this thread is responsible for. So we calculate it like this. We say row is equal to block ID times block dimension plus thread offset. Now, since in our example we only have one block, then block ID X and Y are both 0. So we have 0 times 0. So that those first two terms go away. And then we have the thread offset within the block. So simply the row is going to be where the thread is located at X and Y. We just iterate over n, right? We go from 0 to 2, so that's 3 times, incrementing the iterator. Then we plug into it for example, A, we plug into it the row times n plus k. So that's just stepping through the memory locations, right? Multiply the two together, add them to the sum. So the sum is the dot product of two vectors. You'll see in a minute you do one row by one column, the same row by the next column, so forth. So you do that 9 times. Slide is basically just our main function. We have the constant n equals 3. That's going to be the dimensions of our input and output arrays. So we initialize them to small numbers 1 through 9 to make it easy to work with. Okay. Next, we allocate memory on the GPU. So we use the CUDA malloc function. Like malloc you have on the CPU, CUDA malloc you have on the GPU. So we pass to it the pointer, the address of where we want to put it, and then the size is going to be obviously the number of elements times the size of each element, and then star DA, star DB, star DC are the pointers to that GPU memory, or device pointers. We have to copy the arrays from the host to the GPU. So we use CUDA mem copy. So the arguments here are, the first is the target, DA, and A is the source, and then obviously you put the same size as before, and then this CUDA mem copy host to device, that says what direction to go in. When we come back, we'll say CUDA mem copy device to host. We talked about earlier. It's worth mentioning twice because it's the most complicated result to grasp. Block dim in n gives us a block with 3 threads in X and 3 in Y, 9 threads in total. Okay, so the total number of threads in the block is multiply everything together. This is grid dim x times grid dim y times block dim x times block dim y. This is trivial, we would say, because the grid is 1 by 1. It's just 1 times 3 is 9. 9 threads. Now, in a real application, you don't normally pick it to be conveniently a multiple of the matrix size. We do that for simplicity in this example. Okay, now we're ready to do the matrix multiplication on the GPU. So we call the matmul basic kernel function. It has the 3 angle brackets to indicate this is a kernel function. We pass in the pointers to the GPU address, and then the number of elements in each matrix. So we have here again block dim NN is 3 by 3, 9 threads per block, and then grid dim 1 thread, 1 block we're going to have. Now here's just the tail end of the program. It's kind of simple. We just copied the GPU memory back to the CPU. We use the same CUDA mem copy, but now the target is C. We have now computed the output matrix, and then DC is the pointer to the matrix in GPU memory. We're now copying it back to the CPU, and then obviously the size, and then the instruction as to which direction is CUDA mem copy device to host. Then we print out the results, and we free the memory. We use CUDA free for each of the 3 pointers. Okay, briefly we'll discuss matrix multiplication before we get into doing it with CUDA code. Many of you already know this. For those of you who maybe don't know linear algebra, here's a very quick introduction to it. It's one of the most confusing things, I think, in working with AI. I have a math degree, and believe me, it's difficult to do this on paper. So thank goodness the computer does it for us. At school, I had to do it with pencil and paper. It's very confusing. So anyway, when we do matrix multiplication, you're running the linear part of the forward pass, right? Do matrix multiplication, take the output, run it through the activation function. That's a forward pass in a neural network. So here's an example here with A and B matrices. Basically, you take each row, like for example, the first one here is blue, multiply it times each column. In B, it's blue one, pink one, and green one. And then you plug those values, and each of those multiplications are called the vector dot product. So your 2 vectors, when you multiply them, gives you a scalar, and the formula below shows where you plug it into the output matrix C. So to illustrate, first we'll multiply the first row. Okay, we're going to multiply it times these 3 columns. Well, how do you multiply it times 3 columns? Well, here we just multiply by 1 column at a time. And here you can see this is why, this is where CUDA shines for us. It does this in parallel, so we can do all this at the same time. That's the whole reason that we have these GPUs. Okay, so we've done the first one. Now we move on to the second one. Second column being pink. And then we move on to the third column being green. So then we have 3 values here to plug into the first column of the output C. So we just repeat that. Take the pink column, take the pink row, multiply it by the 3 columns, then plug the output into the next row of C. Then we do the last one. Now we've done all 3, and we have all the values to plug into the output matrix.